It's busy. Now, as that immature cell leaves the bone marrow, enters the bloodstream, begins to circulate around the body, it will continue to make these products. As it begins to fill up its cell with the hemoglobin, y'all laughing at me. That's all right. I like it. It'll begin to fill up that cell. And then it goes, nucleus, endoplasmic reticulum, Golgi. I just don't have any more room. Y'all got to go. And it'll spit them out, literally. And then we end up with a cell that looks like it's going to have little pieces. It's almost at maturity. We're now at site, okay? But almost at maturity, we're going to say not quite there yet. Reticulo. We're waiting for it to come up, okay? Reticulo meaning the structure it has, what it looks like. Because reticulo looks like a mesh, basically a mess in all reality. And then it's mature. And we have our erythrocyte. As we saw, we produce a lot of these every day. Does anybody remember some of those numbers? It was like millions and billions. I mean, huge. Remember, I was like, I'll take any of these in the money cart, So, now, in looking at that, okay, something has to happen. Even though we are, making these cells, how does the body know to make them? It's really cool how the body knows.
Really, chemical signals.
Sort of, yeah. But one of the biggest ways that the body is going to know to make these cells. When we look at the heart and the blood exiting the heart, this huge aorta, once again, we have the branching leading to the head and upper arms. We have the aortic arch that begins to descend. When it begins to descend, what organs does it hit first on its descent?
Like to go down.
To go down. The kidneys. If you look at this structure, as it begins to flow downward, descent, kidneys. The kidneys, based on their structure and their job that they're going to do, they have the ability to pick up on oxygen levels. So, if they're not where they should be, they actually secrete a hormone. Yeah, kind of one of those organs that are, is sort of endocrine, but not. Okay? So it will release erythropoietin. That's the chemical. EPO is what they call it. That EPO is going to go to the bone marrow, to the colony-forming units that have receptors. And we'll say, let's make some cells. And it does. So, this is how we're going to get to keep that cell production high in the body. Or maybe I shouldn't say high, but in homeostasis for the body. So now, the hemoglobin. If you remember from bio and so forth, when we make a protein, that protein is coded for by a gene on a chromosome in the DNA of our cell. The gene says, the A's, T's, G's, C's, all that sort of stuff, okay? And that, gets to lead, gets to make the mRNA strand, blah, blah, blah. As we string together our amino acids, okay? String them, string them, string them, string them, based on the code from our gene. Well, if you remember, we have a primary structure, secondary structure, tertiary structure, quaternary structure. Primary structure is simply amino acids strung together. Those amino acids, if they twist or bend, that's the secondary structure. That twisting or bending, if it folds in on itself, is my tertiary structure. When I have two or more tertiary structures together, I have a quaternary structure. My hemoglobin is quaternary. In other words, I have 2 alpha and 2 beta, and together they look like 4 together. Does everybody kind of see that? So hemoglobin is a very special structure. The code for it, in other words, those bases on the DNA strand, don't quote me on it, I have to look it back up. It's only like 140 some bases. It's not long at all. It's very short. But that's because we need to make a whole bunch of it in a short amount of time. Okay? What can go wrong with the making of the structure of hemoglobin that results in a very debilitating disorder for people?
Sickle cell.
Sickle cell. Sickle cell, on that roughly 100 and, I can't remember, I'll have to look it up. That short string, the number 6 amino acid, is wrong and results in that debilitating disorder that affects multiple areas of the body. So if the hemoglobin is coded for correctly and we end up with this proper structure where I have 2 alphas, 2 betas, we can see that they can bind, each one of them can bind a heme group, hemoglobins. Does that make sense? Okay. The heme group can attach an iron. Okay, so if this is my globin.
Did you say an iron or an ion?
Iron.
Oh, okay.
Iron. I-R-O-N, and not like you do for clothes. Okay? An iron atom. So, if I have the ability on the normal hemoglobin to have 1, 2, 3, 4 heme groups that can attach an iron, 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 iron is attracted, or oxygen is attracted to iron, however you want to say it. Okay? That tells me that one hemoglobin has the ability to carry 4 oxygens. Does that make sense? So, I'd be afraid to give y'all the number of how many hemoglobins are in one red blood cell. Millions. Think about the number of oxygens that's carried. Is everybody with me? So, oh, there's my, somebody tell me my compass work there? See, I said 146. Okay, so, but that's what I'm talking about for those amino acids. That's not long at all. Trust me on that. So, we can carry up to 4 oxygens for every hemoglobin. This is the part that I said earlier about the CO2. CO2, if it's carried on the hemoglobin, will attach to a globin, not my heme group, because that wants to stay available for oxygen. So, for the most part, the majority of our CO2 has to be carried in the blood as the buffered molecule. So, this is how we're going to carry that oxygen. Now, fetal hemoglobin, in other words, while in utero, the fetal hemoglobin is a little different. Babies will keep that hemoglobin with them until about 2 to 4 months after they're born, and then it all switches over to what you see here. But think about this. Egg and sperm meet, fertilization occurs, offspring begins to develop. The cells are requiring tons of energy. So the fetal hemoglobin allows that building of those cells to extract more oxygen from the mom's blood and therefore help with the energy needed for the development of the offspring. So fetal hemoglobin is a little different. Once the baby is born, roughly I think 2 to 4 months of age is when it's all of now in adult, what we call adult hemoglobin. So this hemoglobin has the ability to carry 4 oxygens. If it does, we call it 100% saturation. I'm sure you guys have seen pulse oxes, the little thing they put on people's fingers, which yes and no, okay, but a good indicator of what their oxygen levels are for the body as a whole, okay, not necessarily what that one little red blood cell has, okay, so there's a little bit of a difference, but for the most part it gives us a good idea if a person's oxygen levels are low, okay, that something needs to be done. Do you happen to know at what point of saturation the numbers will drop to before they want to begin doing something? Usually, well, they don't really want to see it go below 95, and usually if it begins to waver below that, they'll begin to give the person oxygen and so forth. But a lot of times, even those of us who are just out here now, as we're just sitting here, do you think we're keeping our oxygen level close to that 95 and higher? No. Why? How many of us deep breathe? No. Do? All the time? 24/7?
No. It's stressful.
I know, right? So a lot of times we're just doing shallow breathing. Okay? We're not doing our where the abdomen actually stretches out and everything. So if we were to have a little pulse ox on, you might see it drop down to 90 or 85 or something, and you're like, oh, breathe. And you see the number go back up. Just saying, you know, if you get one. Anyway. Okay, so the iron that we need, okay? The iron that we're going to need on that heme group, on that hemoglobin, okay, we're going to need to get from our diet, what we eat, okay? People always ask me, I guess because of what I teach and everything, you know, I always get asked questions, and not just here in school. I'm talking, you know, like out of school and everything. I try not to tell people what I do because then they can ask me questions like I'm a doctor or something. And I'm like,